Hello. Today I will be teaching you about the techniques of integration. So, when you are learning about integration and how to integrate a function that you're given, one of the first techniques of integration that you're going to learn about is called the substitution rule, or it's also called U substitution. So, in general, when are you going to use U substitution? You're going to use U substitution when you have a function that looks like this. The integral of f of g of x, g prime of x, dx. So what does this mean? You're going to have an outer function f and an inner function g. And the derivative of the inner function, or something that looks like it, is present as a multiplication to the outer function. So for example, I could have cos of, let's say, x squared, and then I'm going to multiply by 2x dx. So something that looks like this: an outer function, an inner function, and the derivative of the inner function. This 2 doesn't have to be here, because I can make it into a 2 if it's not there, and just divide by 2. So for example, if this was my function without a 2, I would make it a 2 and divide by 2. And this would be the same thing. So why does this work? Well, here's why. When we let u equal the inner function g of x, we can differentiate this du dx equal g prime of x, right? The derivative of g is just g prime. It's just general function. And if I isolate for dx, I'm going to have dx equal du over g prime of x. And notice, if I substitute here dx to be du over g prime of x, so I'm going to go over here. First of all, f of g of x is going to be u. So this is going to become the integral of f of u, g prime of x, this is still there, dx becomes du over g prime of x. And these two will cancel out, and you're going to have an integral f of u du, which is a very simple integral. So for example, if this became, let's take our original example. If this became cos of u, then the integral of cos is sine. So this will become the integral of cos of u du, and this is just going to become sine of u. And then you would put back whatever u was. So in this case, u would have been x squared. If this is unclear, let's look at an example. Example 1. Integral of x cubed cos of x to the 4 plus 2 dx. So right away, I'm looking at this and I know it's U substitution, because I can easily tell that this is an outer function, this is an inner function, and the derivative of this is 4x to the 4. 4x to the 3, 4x cubed. Derivative of this function is 4x cubed. I don't have a 4x cubed, but I told you it doesn't matter, because I can just make this 4 and divide by 4 in the front. So I'm going to let u equal the inner function, x to the 4 plus 2. du dx equal 4x cubed. I'm going to isolate for dx. So dx equal du over 4x cubed. So now I have a fourth, the integral of 4x cubed cos of, well, this is u, and this dx became du over 4x cubed. And this is how you know you did it right. In u substitution, you're always gonna cancel like this. So now I have a fourth, the integral cos of u du. This is a very simple integral, of course. The integral of cos x is sine x, so the integral of cos u is sine u. So I'm gonna have a fourth sine u plus c. You always have a plus c when you're doing indefinite integrals. I started with x and now I'm left with u. So I cannot leave it like this. I have to substitute back what u was. So a fourth sine of x to the 4 plus 2 plus c. I can check my work by differentiating this and seeing if I get this function back. So let me do that. This is the chain rule. So derivative of sine x is cos x. But I don't have x, I have a function, x to the 4 plus 2. And now I'm going to take the derivative of this function. I have a fourth. Derivative of this function is going to be 4x cubed. And now this 4 cancels this 4. And now I'm left with x cubed cos of x to the 4 plus 2, which is x cubed cos of x to the 4 plus 2. So this is how you know you did it right. The derivative of c is nothing, which is why you need to add it, because this can be a plus 2, a plus 3, a plus whatever. It's always gonna be 0 when you differentiate back. Let's take another example, a harder one. Integral from 1 to 2. This is called a definite integral. When you're given limits of integration. Square root of 1 plus x squared, x to the 5 dx. I notice a bit of a problem. Right now, my inner function is this. My outer function is the square root. I don't see the derivative of the inner function right away. The derivative of this function is 2x. I don't see a 2x here. But I can split it off. So, integral of 1 to 2 square root of 1 plus x squared, x to the 4 times x. So I split this x to the 5 into an x to the 4 and an x. And why did I do that? Because now I have the derivative of the inner function, 2x. Remember, I don't have the 2, but it doesn't matter. I can put a 2 and divide by 2 here. What about this x to the 4? Well, let's see. Let u equal 1 plus x squared, the inner function, du dx equal 2x, dx equal du over 2x, right? So this is important, this is important. And what about this x to the 4? I see an x squared here. If I solve for x squared, I have x squared equal u minus 1, right? This is not x squared. If it was x squared, I would have just let it be u minus 1. But I can make it an x squared, right? This is, I have my x squared now. This is still x to the 4. integral from 1 to 2. Now I have the integral from the square root of u. This x squared is u minus 1 squared, and this dx, I'm going to leave this x for a moment, and I'm going to put this dx equal to du over 2x. Now I'm going to cancel this x with this x, and I'm left with a half. I'm going to put this half at the front. So I'm going to put it here. You notice I'm not putting from 1 to 2. This is because when you're doing u substitution with definite integrals, you need to change the limits of integration, right? Because these limits are based on x. So when x equal 1, when x equal 2, when you're moving from x to u will be different. So what are the new numbers? Well, I can get them from right here. U equal 1 plus x squared. This x used to be 1 to 2. So I'm going to put 1 for the lower parameter, squared. 1 plus 1 squared is 2. This is 1 plus 1 equal 2. Now u, for the upper parameter, it used to be 2. So 1 plus 2 squared. And this is 1 plus 4, which is 5. So the lower one became 2, the upper one became 5. I'm going to expand this next. Equals a half, integral from 2 to 5, right, new limits. I'm going to put this into the other form, which is u to the power of a half. And you'll see why in a moment. This becomes u squared minus 2u plus 1. This is du, right? This 2 became here. These x's cancelled. I'm left with a du. This expanded. This is u to the half. I'm going to multiply this u to the half in. So equals a half integral from 2 to 5. This a half u to the power of a half times u squared. When you're multiplying with the same base, you can add the exponents, right? From grade 9. So 2 plus a half, 4 over 2 plus 1 over 2, 5 over 2. So u to the 5 over 2 minus 2, u to the 3 over 2 plus u to the 1 over 2. Right? U to the 1 over 2 times 1 is just u to 1 over 2 du. Now this is just a simple polynomial which you know how to integrate. The rule for integrating a simple polynomial like this is you add 1 to the power and you divide by the new number. So equals a half u to the 7 over 2 divided by 7 over 2 minus 2 u to the 5 over 2 divided by 5 over 2 plus u to the 3 over 2 divided by 3 over 2. And if this were an indefinite integral, I would add plus c and substitute back what x was, or sorry, what u was. So I would put 1 plus x squared here, and I would add a plus c and I'd be done. But since this is a definite integral, I need to continue to simplify this. First of all, I'm gonna reciprocate this. So instead of dividing by 7 over 2, I'm gonna multiply by 2 over 7. And I'm also gonna multiply this a half in the same step. So I have a 2 over 7 and I have a multiplication by a half. So the 2 over 7 would divide by 2 to make a 7th, u to the 7 over 2. I have a 2 over 5 multiplied by this 2 to make it 4 over 5, but I'm also having this divide by 2, so it's going to be 2 over 5. So minus 2 over 5, u to the 5 over 2. Plus, I have a 2 over 3, right? Multiplied by 2 over 3, and I have a 1 over 2 here. So when I multiply those two numbers together, I'm going to be left with 1 over 3. And I'm going to take this from 2 to 5. So I'm first gonna put 5 here everywhere, and then I'm gonna do minus, and then I'm gonna do 2 everywhere. So this is what it looks like. Equals a 7th, 5 to the 7 over 2, minus 2 over 5, 5 to the 5 over 2, plus a third, 5 to the 3 over 2. So this is the 5 part. I'm going to do minus. And then instead of 5s, I'm going to put 2s everywhere. So a 7th, 2 to the 7 over 2, minus 2 fifths, 2 to the 5 over 2, plus a third, 2 to the 3 over 2. Now I can simplify this further, and here's how I would do it. First, I notice this 5 to the power of 3 over 2, I can factor it outside. But what is 5 to the power of 3 over 2? Well, this half here is like a square root. Would you agree? And this 5 to the power of 3 is 125. So I have a square root of 125. And I'm going to factor this outside. So I'm going to be left with plus a third in the third term. And in this term, if I factor a 5 to the power of 3 over 2, that's the same as dividing 5 to the power of 3 over 2. And you know that when you're dividing exponents, you subtract. So this is going to be subtracting 3 over 2. And 5 over 2 minus 3 over 2 is just 1. So this is 5 to the power of 1. So it's just 5. And you have 5 divided by 5, so you're just left with 2. And the same thing here. When you subtract 3 over 2 from this number, you're left with 4 over 2, which is 2. So you have 5 squared. So 25 over 7. And I'm going to do the same thing here. I'm going to factor out 2 to the power of 3 over 2, which is square root of 2 cubed, which is square root of 8. Square root of 8. I'm going to be left with a third in the third term. Here, 5 over 2 minus 3 over 2, once again, just 1. So I'm left with 2. So this is 4 over 5. And here, I'm going to do the same thing. Subtract 3 over 2. I'm going to be left with 4 over 2, which is just 2. So I have 2 squared, which is 4. So I have 4 over 7. Now, this is going to simplify to 40 over 21. You can see the denominator is 21 because 7 and 3. So if I convert this to whatever it is over 21, right, it would be 75 over 21 and 42 over 21 and 7 over 21, and add and subtract all those numbers, I'm going to be left with 40. And this root of 125, I'm going to simplify it to 5 root 5. So I have 5 root 5, 40 over 21. And this root 8 is 2 root 2. And this inner part simplifies to 11 over 105. So I have 7 times 5, 35. 35 times 3 is 105. So that's how you get the denominator. And of course, you know how to add fractions. So now I'm going to put 40 times 5. So 200 root 5 over 21 minus 11 times 2, 22 root 2 over 105. So I'm going to multiply this by 5 and simplify this to become 1000 root 5 minus 22 root 2 over 105. And I can check my answer on the calculator. First, I'm going to do 1000 root 5 minus 22 root 2 over 105, approximately 21. And I'm gonna check the limits of this function. 1 plus x squared multiply by x to the power 5 from 1 to 2. And it's approximately 21. It's the exact same. But notice how I got an accurate answer here when my calculator can only estimate. It can only give me the decimal. It cannot give me this exact number. I hope you enjoyed this lesson. And I hope to see you again next time. Bye bye.